Correct. That'll be the first thing we talk about today, and I just wanted to write this down as I had 5 minutes before class started. So, yeah, haven't missed anything. There are some exams that weren't picked up yet, and a few homework sets. See Rosales, Richardson, Navarro, Gutierrez, Edmonds. So, if you guys are here, just pick up your old work. Also, don't forget to turn in the homework that's due today. And by the way, this example problem is up here on the board. We're not ready to talk about that yet. I just had a couple extra minutes at the beginning of class, so I thought I would just write that down now, but we're not there yet. Okay. All right, so good morning, everybody. Just before we begin, again, a reminder that the homework that's due today, you should add to the pile up here at the front. I'll post the solutions outside my office when I get back to my office after class, as usual. Also, let me just remind you that the homework that you're turning in now is the last homework set you're actually going to be submitting as part of your homework grade. You still have 2 full sets of homework that I just wrote on the board last time as the last homework set. And even though I'm not going to be collecting those, you still need to do them. I will post the solutions no later than next Wednesday to give you a full week prior to taking your final exam. And of course, your final exam is 2 weeks from today. Not that you want to hear that already, but it is. And it'll be the same format as the other exams. So open nothing, right? It's a closed book, closed notes exam, except you can use your 3x5 note card, just one 3x5 note card on both sides with equations and diagrams only, and of course a property table handout, including the psychrometric chart. That'll all be what you'll be allowed to use on the final exam. So, certainly think about that. I'll also let you know well in advance that I do tend to emphasize on the final material that you have not yet been tested on. So certainly anything from the entire class could be covered, but material like what we're talking about now on air conditioning and next week on combustion, you can most certainly expect to see at least one problem of each of those types on your final. So please don't let yourself fall behind so late in the quarter. Most of you, I'm sure, are keeping up with the class. All right, so we're now continuing the discussion of various air conditioning processes. And specifically, we're now talking about dehumidification by cooling. Now, just in summary from last time, if I show the psychrometric chart, when we talk about dehumidification by cooling, basically we would have some sort of an air conditioning system where we would have flow in at point 1 and flow out at point 2, but there's going to be some sort of a cooling coil, and there's going to be a certain amount of heat that's going to be rejected from the system. So if we just assume that point 1 was over here, as we remove heat, first I would note this is just simple cooling, but not quite, right? It's simple cooling until we get to the saturation line. But in this particular case, when we're talking about dehumidification by cooling, we're going to continue the cooling process. And since we already understand that the amount of water vapor that can be held in air is a function of the temperature, as the temperature drops below the saturation, which is your dew point temperature, right? Well, then water is going to have to condense out of the air. The cooler air can't hold as much water. So the condensation is going to occur once we hit the dew point until we get down here to state point 2. Right? And of course, since condensation is occurring, there's going to be a certain amount of water that's going to be draining out the bottom of this particular system. So this is the basic dehumidification by cooling setup, and this should already be in your notes from last time. I also want to note that the water temperature is actually something we can estimate pretty accurately. We would note that all the condensation is occurring, right in here, right? So this condensation, well, it'll have the average value between when condensation begins, which is the dew point temperature, and when condensation ends as we leave this particular device. So this is just going to be the dew point based on my inlet conditions, and then plus T2 divided by 2. So this is going to be the water temperature. When you look at some of the problems that are discussed in the book, for some reason the author simply gives you that information for most of the problems. The author will say, assume that the water temperature or the condensate temperature or something like that is X number of degrees. That's not particularly accurate. So, I mean, it could be accurate if the author had given you the right numbers, I suppose. But in the several problems I've looked at, I mean, he'll give you numbers like where the condensate is even lower than T2, which is technically impossible. But nonetheless, if the author gives you a water temperature, just use it in the problem statement. But if not, then just realize you'll have to calculate it this way. Also, let's remember that we've already done our mass balances. And we saw these last time, again, both for air and for the water. We certainly understand that the amount of air that flows in at 1 and at 2 is the same. So we're just going to call this m dot A. So this is our mass balance for the air that we've seen. And with regards to the water, we've already seen that the rate that water is leaving the system is really just the difference between the amount of water that was in the air entering at point 1 and the amount of water that's remaining in the air as we leave at point 2. So this is just going to be omega 1 minus omega 2. Again, m dot A times omega 1 represents the flow rate of water vapor coming in, and m dot A omega 2 is the flow rate of water vapor going out. I mean, how could the amount of water that condenses out of that air be any different than the difference between what we have going in and what we have coming out? So, you know, that's a pretty obvious set of equations here. Now let's look at our energy balance. And when we deal with the energy balance, let's again keep in mind that we're just using the first law for a steady flow process. And, you know, as such, we have the possibility of multiple inlet and exit streams. So we would just simply note that, you know, whatever goes in has to equal what comes out, right? The energy that's coming in is the energy associated with the inlet flow. The energy that goes out, well, there's actually three terms here, right? We've got heat that's being removed from the system. I mean, that's what's causing condensation. Well, the temperature drop causing condensation. You know, we've got liquid water with some energy coming out, and we've got the air that has energy going out. And, you know, of course, based on our first law, it's just the sum over all inlets, m dot IHI equals the sum over all exits, m dot EHE, then plus the heat transfer rate, right? So the energy balance would then just be m dot AH1. So that's what comes in. Remember again, H is for the mixture, but the data from all of our, well, from our psych chart or from our equations is per unit mass of that air. So, I mean, certainly we had to multiply by the airflow rate. Even though it's the mixture, it's still the airflow rate that we use. And coming out then, well, we'll have an m dot AH2. We'll also have the liquid water, the condensate term. So that's just going to be m dot WHW. And then we would also have the heat transfer rate, so plus Q dot out. So that's our basic equation. And then typically we reorder this. I mean, if we're designing an air conditioning system, we typically would know what is considered comfortable conditions. I mean, we would know what point 2 is. We'd estimate what point 1 is, let's say based on some bad day, you know, nice hot humid day you're having in that vicinity. What you need to do is figure out, well, how much heat do we have to remove? I mean, you have to provide a refrigeration cycle, right? This refrigeration cycle, this Q out, is the heat that goes into what? The evaporator of a vapor compression refrigeration cycle, right? So, you know, think about this stuff, that the refrigeration cycle is here. We're just dealing with the air conditioning device that has a refrigeration cycle as part of it. Nonetheless, as a good engineer, you need to know what the heat transfer rate is so you can properly design that refrigeration cycle. Nonetheless, let's rewrite this. So Q dot out is just going to be m dot A. And then here we would have, what, an H1 minus an H2 term. But then we also have the water term. So we have minus m dot w hw. Okay. Then what we would typically do is simply plug in our mass balance up into here. So plug in from above. And Q dot out then. Well, first of all, you can see that all three of these terms are going to have an air mass flow rate term attached to them. So we'll just bring that out. And then H1 minus H2. And then minus, well, this would be m dot A, which comes out. And then omega 1 minus omega 2 times HW. Okay, so this is the equation that we would utilize in order to figure out the rate of heat rejection. So that's an important equation. Of course, this one's important. I mean, they're all important. So this is dehumidification by cooling. Now, let me note one thing. When we do use dehumidification by cooling, which is very common, we're left with saturated air. Saturated air, well, that has high humidity, right? I mean, if we're right on the saturation line, then regardless of the temperature, that air holds as much moisture as it is capable of. And sometimes that amount of water in the air is actually too much. You know, we would feel that as being uncomfortably humid. And as such, it's very likely that we would then want to reheat this air. So that's typically what we would do. In a typical problem, we don't just deal with the dehumidification by cooling, but then we also add to it a simple heating process. That'll bring the temperature up to a more reasonable value, but it will also drop the relative humidity down to a more reasonable value. So again, this is often used in conjunction with reheating in order to drop the relative humidity and increase the temperature. Okay. Now, I would like to go through the example problem. So first, any questions just in general on this particular concept? So here's the example that I'm going to do. It was actually modeled on problem 14-85 from the 7th edition of your textbook. I believe that's one of the example problems that I actually had copied and is on Blackboard if you want to look at the way that this problem was originally stated. But I'm modifying it a little bit. I'm basically giving us a flow rate going into the system. And in the book's problem, they're asking for, you know, heat removal per unit mass or heat addition per unit mass. That's not what I want to do. I want to look at a more complete problem. You know, if we know the volumetric flow rate moving through that particular device, I want to know the actual rate of heat removal in the cooling section and the rate of heat addition in the heating section. So basically, we have an air conditioning system that's drawing in 1 cubic meter per second of atmospheric air with the conditions at 1 atmosphere pressure, 34 degrees C, 70% relative humidity. So that's kind of warm, humid air, right? I mean, 34 degrees C is what, about 90 degrees or so? So that's hot. Anyway, the air is cooled and dehumidified, and then it is reheated. Okay, it's heated to 22 degrees Celsius and 50% relative humidity. I mean, that's nice, right? 22 degrees Celsius is what, about 72 degrees Fahrenheit. Nice, modest relative humidity. I mean, that's comfortable air. So what we want to do is find the air temperature before entering the heating section, in other words, at what I would call state point 2. And the rate of heat removal in the cooling section, and the rate of heat removal, the rate of heat input in the heating section. So the first thing we want to do is recognize that since the given pressure is standard atmospheric pressure, certainly we're allowed to use a psychrometric chart. If we want to show it on a psych chart, and I'll just keep this one up on the board, but you should redraw it in your notes. We're basically going from point 1 to point 2 in the dehumidification by cooling section. So here's state point 1, and here's state point 2. But the process doesn't end there. So this is the same diagram that's over here, but we have reheating. So now we're moving through the next section. And let's say that we leave at 0.3. And then here we've got some other heat exchanger. And this is the rate of heat input. Okay. By the way, the rate of heat input is also important. If you have this type of a system in your facility, your building, whatever you're working on, we also need to know how much heat supply we're going to need, right? We have to design some sort of a heating system. Maybe it's a heat pump, vapor compression refrigeration cycle that provides the heat input. Maybe. Maybe it's just a natural gas-fired furnace that provides the heat input. But in any event, you need to figure out, how this relates to the rest of the real world. What kind of fuel supply do we need? What flow rate? What kind of ductwork do we need? How big is the burner going to have to be to release the appropriate amount of heat? Or again, if this is a heat pump, then, where does heat come in from? Well, that's the heat being rejected from the refrigeration cycle. In other words, that's the heat that goes out of the condenser in a vapor compression refrigeration cycle. So this is more realistic. And lastly, let's just show on here that this process from 2 to 3 is really just simple heating. We're not adding or removing moisture, so we'll end up at some state 0.3 over here. And I would say this is probably not to scale. But nonetheless, this is our illustration. So we have our dehumidification by cooling, and then we have our simple heating. Okay. Now, quite frankly, the equations that we're going to use are equations we've seen. Many of them are still on the board, well, until right now. Now they're only half on the board. And some of them, of course, are from previously when we just talked about our simple process, our simple heating process. So let's just look at the type of equations we're going to need. Well, maybe I shouldn't have erased that one. Clearly, if we want to find the rate of heat removal, we're going to have to use the equation that I just erased. So those are equations that are, just behind one page in your own notes. So I'm not going to bother to write that down again. As far as the rate of heat input, well, again, that's just from last time, or I guess the previous time, and that's just the air mass flow rate multiplied by the enthalpy change, right? So those are the two equations we're going to use. Again, the first equation is the same one that we've just seen. So this is just m dot A times H1 minus H2 plus omega 1 minus omega 2 HW. And Q dot in is just m dot A. And this is going to be H3 minus H2. All right? When we looked at simple heating before, we just used state points 1 and 2 as our inlet and exit. Of course, now 2 and 3 represent the inlet and the exit. So clearly, in order to solve these, we need to know what the thermodynamic state is at, well, points 1, 2, and 3. Now, much of this information is already given to me, right? I know T1 and phi1, in other words, the actual temperature, we can call it the dry bulb temperature, as well as the relative humidity. So T1 is 34 Celsius, relative humidity is 0.70 or 70%. We also know the conditions at 0.3. I mean, this is what the air is delivered at. So we're given a temperature of 0.3 at 22 degrees Celsius with its relative humidity of 50%, so 0.50. So we know that data. And of course, having this information, we could go onto our psychrometric chart and look up whatever we want. I mean, clearly we're going to need H1 and H2, omega 1 and omega 2. We're also going to need H3. So here we find omega 1 and H1. Here we find H3. What about omega 3? Well, that's going to be pretty easy to find because it's actually going to equal omega 2, right? Now, quite frankly, we don't need omega 3 at the beginning of the problem. We really just, in fact, we don't need omega 3 at all really in the problem. We're given two properties. We have the temperature and relative humidity. So why did I even bother to write this down? Well, because look at what we have at state point 2. We have nothing given at state point 2. We know that it's saturated, but we have to utilize the fact that omega 2 is equal to omega 3. That gives me the second property at point 2. In other words, we know the fact that it's saturated, and we know the value of omega. Yes?
For that Q out, you wrote positive and that one is negative?
Oh, yeah, it's a negative. Sorry. Yeah, thank you for that. Nonetheless, we know that we're going to need information at point 2. Well, clearly, we have omega 3, so we know omega 2. But we also need the enthalpy at point 2. So we are going to have to use our cycle chart again. So at omega 2, saturated air, then we can use that in order to find the enthalpy at point 2. So now it's really just a matter of going into the cycle chart, pulling out all the data, and going through some calculations. Well, there's really one other calculation we need too, right? And because of that, I actually need a little more data than I've shown on the board. We need the mass flow rate of the air. So the mass flow rate of this air, the air component, not the water component, well, that's just going to be the volumetric flow rate divided by the specific volume. Now, we can find this. I mean, m dot air is constant through the entire system. We have to figure out whether, we have that data at any of our state points. Do we have the ability to find these terms? Well, yeah, sure. We're given the volumetric flow rate at the inlet. So since we're given the volumetric flow rate at the inlet, well, we better use the specific volume at the inlet in order to calculate the air mass flow rate. So we also need V1. All right, so now we can go into the psychrometric chart and pull out the data that we require. The humidity ratio, or specific humidity, if you will, is 0.0238. And, if you have a cycle chart, you can certainly follow along and see if you're getting numbers similar to this. So this is going to be kilograms water vapor per kilogram of the dry air. Then we have our enthalpy term, so we get that to be 95.2. That's kilojoules per kilogram of the dry air. And then the specific volume we can also read. We are going to have to, let's say, visually interpolate or estimate, but this becomes approximately 0.903 cubic meters, again, per kilogram of the dry air. So that's our data we need at point 1. And again, if anybody is finding different values when you're looking at the cycle chart, please let me know. It's certainly possible that I've read some data incorrectly. Now we move on to state point 3. So the enthalpy is 43.1 kilojoules per kilogram of the dry air. And then omega 3 we can read off, and that's 0.0082. So again, kilograms of water vapor per kilogram of the dry air. And then lastly, we know what omega 2 is. We know this value, so we can just look up the data. We need the enthalpy at state point 2. We just move along the saturation line until we get to the value of omega 2, which equals omega 3. And again, just pull off the data we need. So what we find here is that the enthalpy at 2 is 31.8 kilojoules per kilogram of the dry air. I might note that the author has asked us to find the temperature at this point. So as long as we're in the cycle chart, we really have two things we can do, right? We can either read off the wet bulb temperature at point 2, or we can read off the dry bulb temperature at point 2. I mean, at saturated air, the two numbers are going to be the same. So either way you do it, you'll get about 11.1 degrees Celsius. So I'll just put that down here. T2 is 11.1 degrees C. All right, so this is the majority of the data we're going to need. I am going to have to find the dew point, right? Because I need to find the temperature of the water so that I can get the enthalpy of the water. So that's going to come next. Yes?
When we're doing a problem like this on the final, how are you going to solve it for reference? Are you going to be like calculating the numbers or reading off the cycle chart? Is the cycle chart similar, but
right.
noticeably different?
I do both. I mean, typically I would kind of use, tables, but then I would also look at the psych chart. But the numbers are pretty much the same. I mean, quite frankly, as I'm grading this, as long as your numbers are close to mine, within, let's say, 10 or 15%, something like that, then I'll assume that you read the chart properly. So yeah, don't worry about whether you're being absolutely and completely accurate. Just do the best you can. And, if you just write the words from the psych chart, or I've even had students who've attached the psych chart to their exam and shown points 1, 2, 3, whatever. I mean, you could do that too if you really want to. It wouldn't be required, but you could. Anyway, any other questions? Yes?
Finally, you would let us choose which method?
Yeah, sure. I mean, you can always use the various equations. Now that we understand that we have a psych chart and we know how to use it, I mean, certainly it's easier to just pull a handful of numbers off the psych chart than to have to go through multiple equations, dealing with all sorts of things like partial pressures and looking up saturation temperatures and everything we talked about a couple of weeks ago. I mean, yeah, that's interesting, but why waste the time? So, yeah. All right, so continuing then, let's find the temperature of the water, which means we need the dew point. So here's the dew point at point 1. In other words, the dew point of the atmospheric air in this particular problem. So again, we'll just have to go into our psych chart. We just move horizontally until we hit the saturation line, and then just simply read off the temperature. And again, because it's saturated at that point, it's either the wet bulb temperature or the dry bulb temperature. It gives you the same result. Nonetheless, the dew point, as I read it, is about 27.5 degrees. So again, those following along, hopefully you're getting the same thing. And now we can find the temperature of the water, which of course is pretty straightforward. And this is 19.3 degrees Celsius. And since we know this, then we can now go into our property tables and look up the enthalpy of that water. So HW is just the enthalpy of the saturated liquid at that particular temperature. And as usual, we'll have to go through some interpolation, but we end up with HW of 80.98. Well, of course, this is from table A4, right? So 80.98 kilojoules per kilogram, and this is of the water. All right, so now we have our enthalpy data. Let's calculate the air mass flow rate. I'll just put the numbers in. So 1 cubic meter per second divided by 0.903 cubic meters of the mixture per kilogram of the dry air. And we get an air mass flow rate of 1.107 kilograms per second. And now we can finish up the problem and get our final results. So Q dot out equals, and I'm just going to plug the numbers into those equations. So 1.107 kilograms per second. I should again put that this is a kilogram of the dry air just to make sure that's appropriate. And then all of our other terms, so 95.2 minus 31.8 kilojoules per kilogram of the dry air, and then minus 0.0238 minus 0.0082. This is kilograms water vapor per kilogram of dry air. And then we multiply that by the enthalpy that we just found. So 80.98. And this is kilojoules per kilogram of water. So the water terms, of course, are going to cancel. In fact, the air terms are going to cancel. We end up with kilojoules per second, which is what we need. Anyway, let's close the brackets and do the math. And we get 69.44 kilojoules per second. Okay. So we need to make sure that we have the ability to remove this much heat every second. And then the rate of heat input in the reheat section, well, again, just m dot air. And then multiplied by the enthalpy difference from 2 to 3. So 43.1 minus 31.8. And again, the air mass cancels, and we end up with 12.51 kilojoules per second. Okay. So there's that. What if I'd asked you a different problem? What if I had said that the heat rejection is to a vapor compression refrigeration cycle that has a coefficient of performance of 10, and I want to know how much power is required by the compressor in the refrigeration cycle? You could do that pretty easily, right? If we know the rate of heat rejection, we know that the coefficient of performance is just, well, it's a measure of the relationship between the amount of heat that is rejected versus, or heat would actually be input in this particular case, you know, to the amount of work that's done or the amount of power. So if you're given the coefficient of performance, yeah, knowing the rate of heat transfer, you can very easily find the work required by that compressor. Well, so think about these kind of problems too. Anyway, there's your example problem. Are there any questions on this? Okay. All right, so the next thing that we're going to talk about then is what we call evaporative cooling. And evaporative cooling is also one of these air conditioning processes that is very common. Perhaps most of us don't really think about evaporative cooling because here in the LA basin, or really anywhere in this part of Southern California, we just don't use evaporative coolers. The air here is generally just too moist, right? We're close to the ocean. The prevailing westerly winds generally bring moist ocean air onto land. So the air's not dry enough really to use evaporative cooling. But if you're on the other side of the mountains, right, in any of the deserts, well, there it's not only very hot, but it's also very, very dry. There's not much moisture in the air. The mountains keep the coastal moisture, well, on the coastal side. So it makes sense to use evaporative cooling there. In fact, in those areas, typically this would be called a swamp cooler. Technically, it's called an evaporative cooler, but it's also called a swamp cooler. So let's talk about evaporative cooling. Okay. So let's say you have very, very hot but very dry air. Is there some way that we could cool that air down in a cheap and efficient manner? Now, sure, we could use a refrigeration cycle, right? We can use that as part of our air conditioning system, and anybody who lives in the desert and who operates their air conditioning all the time knows that in the summertime you're spending, what, $300, $400, $500 a month just on electricity bills, right? Do you really want to do that? I mean, do you really want to run a compressor of a vapor compression refrigeration cycle in order to remove the appropriate amount of heat to keep the air cool and comfortable? Well, you don't have to. If the air is dry, can't you just squirt water into that air? And as that water evaporates, well, it needs energy from somewhere. It gets the energy from the air. The air actually cools as the water evaporates into that air. Now, granted, during an evaporative cooling process, the humidity is certainly going to rise, right? As the water evaporates into the airstream, then, well, the absolute humidity is certainly going to rise. It is possible with the swamp cooler that you could end up with very, humid but much cooler air. Quite frankly, most people would probably prefer air at 70 degrees Fahrenheit, even if it's saturated, to air at 110 degrees Fahrenheit or 120 degrees Fahrenheit or whatever it gets to be out in the desert. No matter how dry it is, it's just too hot. So let's talk about evaporative cooling and how this particular process works. So again, let's say that this is my air conditioner or an air conditioning process, and we have state point 1 that enters, and state point 2 is what leaves. And then what we're going to have is water that's going to enter through a whole bunch of sprays. Now, there's actually two ways to do this. I mean, I show this as if this were a bunch of spray nozzles. But there's actually another way you could do it. You could just use the capillary action of a liquid on a wick, or actually a big giant wick or a series of wicks. Think of wicks as just a whole bunch of shoelaces. You could have a pool of water rather than spray nozzles, and then just have all these wicks, these literally hundreds of shoelaces hanging into that water, and then the water is just going to soak up onto the wick, right? And then the air is going to blow across that. It performs exactly the same function as does sprays. So these are going to be sprays or wicks from a pool of water. It really doesn't matter. I guess shoelaces are a lot cheaper than water spray nozzles. So you don't even have to use shoelaces. You can just use old rags or cloth or anything you want. I mean, people have actually made their own swamp coolers out in the desert, and they cost almost nothing. I mean, a pool of water, a big tube, or some duct work, there you have it. So how does this system work? Well, before I even show this on a psych chart, let's look at the equations that are involved, and then I'll show this on a psych chart. So first of all, we would have to use our mass balance equations, and as usual, with regards to mass balance, the amount of air that comes in, the dry air component is going to be the same as the air that goes out. So m dot air at 1 and m dot air at 2 and m dot air are both going to be the same. And then with regards to the water, well, here we should be able to understand this, right? I mean, again, this is just a mass balance. We have a certain amount of water coming in at 1. Now that's water in the airstream. So I would just call this m dot a omega 1. So that's the water vapor that comes in along with the air. We also have water that's being added. I'll just call that state point representing the water just W. So plus m dot W. And this is going to have to equal the amount of water that leaves. So that's just m dot a times omega 2. And then what we can do is rearrange this just a little bit and note that m dot water is then just m dot air, and then multiplied by the difference in the humidities. So omega 2 minus omega 1. So this is going to give you a value for the amount of water that you're going to need. Again, this is important, right? You need to make sure that you have enough water supplied to your spray nozzles or to your wicks every second so that you can then undergo the appropriate evaporation process. All right, what about the energy balance? Okay, so again, the energy balance should be pretty straightforward too, right? We have, well, there's no heat transfer. We're not adding heat, we're not removing heat, so those terms aren't there. All we really have are the 3 terms associated with the problem, right? We've got water coming in, and we've got air coming in, and we've got air going out. So the energy balance is pretty straightforward. We can write this as m dot W HW, and then plus m dot of the dry air times the enthalpy of the dry air that comes in. And then this has to equal the mass flow rate of the air times the enthalpy that goes out. Again, this is a dry air flow rate. All right. Now we can just simplify ever so slightly. We'll write it this way. And then we want to make an observation. So if we look at typical swamp coolers out in the real world, actually any swamp cooler out in the real world, what we realize is that the amount of water that is added into the system is significantly less than the flow rate of the dry air that's moving through the system. Okay, and this would generally be at least 2 orders of magnitude different. So this is just what we observe, that the mass flow rate of the water is actually much less than the mass flow rate of the dry air. Okay, and as such, we can simply eliminate the m dot W term from the left-hand side of the equation. So we'll then note that m dot W HW is just very small compared to m dot air H2 minus H1. In fact, it's so small that we can approximate this as 0. Okay, is it exactly equal to 0? No, but it's certainly approximately equal to 0. Again, this is just what we find by observation of the real world. And as such, look what happens to the energy equation. Well, basically, m dot A, H2 minus H1 is about equal to 0, and therefore H1 is equal to H2. Now, this is an approximation that can only be made if we're dealing with a swamp cooler type of process. We're not going to estimate that the water flow rate is much less than the airflow rate for any other process, just for this one. Now, what does it tell us if we note that the enthalpy is constant? And now we can look at the psychrometric chart. So let's just say that that's my state point 1. If the process is approximately a constant enthalpy process, and these are the lines of constant enthalpy, as I had stated earlier, and as we've now observed by looking at the psych chart, lines of constant enthalpy are essentially the same as lines of constant wet bulb temperature. Right? So if the enthalpy is constant during some process, then the wet bulb temperature also has to be constant. And again, it's approximate. You can see that the lines of constant wet bulb are not exactly parallel to the enthalpy lines, but they're extremely close. So since the enthalpies are constant, therefore, we could easily conclude that the wet bulb temperatures are going to be constant. All we're doing then is just moving along a constant wet bulb temperature line up towards point 2. Now, we don't know exactly where point 2 is. I mean, point 2 could be saturated. It could be, maybe slightly less than saturated. It certainly couldn't be anything beyond saturated. I mean, you can only get so much water vapor into the air, at which point it's just simply not going to accept any more water. So this is the basic process. And the fact that it's a constant wet bulb temperature actually makes it super easy to do the analysis. So let me give you an example, because quite frankly, there's really no other equations that we need to deal with. What I would like to know is what is the lowest temperature we can get out of a swamp cooler if the atmospheric air is at certain conditions. So find the lowest temperature achievable by a swamp cooler. In other words, an evaporative cooling process with atmospheric air at about 105 degrees Fahrenheit and 15% relative humidity. Now, if you're thinking that there's going to be a bunch of equations for you to solve, well, there aren't. In fact, there's no equations to solve. All we do is use the psychrometric chart. So we have the psych chart here on the board, so we go into the psych chart at the appropriate conditions, right? So here's my relative humidity. In fact, with that low of a relative humidity, maybe I will just redo the psych chart just to try to be a little more accurate. So, relative humidity, 105 degrees, 15% relative humidity. Is going to be down here somewhere. There's state point 1. And then we just follow the line of constant enthalpy or constant wet bulb temperature line. And we just simply read off the value of the wet bulb temperature. So T wet bulb along this line is about 69 degrees Fahrenheit. So that is the lowest possible temperature. Okay. Now, certainly, if you ended up with a slightly different value, that's possible. You don't have to continue to add moisture beyond a certain value. I mean, you could have some sort of a control system monitoring the whole thing, and when the temperature hits a certain value, then you can shut the system down, if you will. But nonetheless, this is the result here. That's pretty good, right? I mean, 105 degrees, 15% relative humidity is kind of typical desert weather, and it's not particularly comfortable. 69 degrees Fahrenheit, even saturated, I mean, that's great. That's kind of like what we've had, pretty much every morning this week, right? We have our 2 weeks of spring before summer hits, right? Welcome to Southern California. But nonetheless, every morning now we have moist air. It comes in off the coast. The temperature is right around there, right around 70 or so. The air is completely saturated. We know that because there's fog in the air, there's dew on the ground. That's pretty comfortable, right? And it costs nothing. Just a big piece of ductwork and a bunch of water and shoelaces, and you've got yourself a swamp cooler. So you could save yourself thousands of dollars every year by using one of these out in the desert instead of an air conditioning system. Okay. So there's a question back here. I thought I saw a hand. Yes?
What's the fifth word in your example called?
Achievable. Find the lowest temperature achievable by a swamp cooler.
Okay.
Yes?
Just on the more practical side, so you keep on saying shoelaces,
Okay.
but I mean, honestly though, when you're calculating the mass flow rate of the water, wouldn't it be a lot easier to have a spray instead? How would you get mass flow rate when you got evaporative?
Well, the fact is, if you have, just a pool of water, it becomes immaterial. Most of the time, if you're running a swamp cooler, you'll just let the thing run and drop to as low as temperature as possible. You just keep the pool full, keep water on the wicks at all times, and that's not a problem. Fortunately, water is really cheap. So, it doesn't matter how much water you really have to add. Whatever needs to be added as you cool down will be added via that system. Now, certainly if you have a spray nozzle, yes, you have a little more control, right? You can measure the rate of water flowing in. That should give you a better feel for, therefore, how much air you could cool, and it'll give you better control over your final, temperature and humidity and all that. But, sometimes one would, let's say, give up a little bit in accuracy for, cost and convenience. If you want to have a control system, fine. But water flow meters aren't exactly cheap, although they're cheaper than other type of flow meters because there's so many of them out there. But still. So hopefully that answers your question. Is there another question dealing with this? All right. And this then brings us to the final topic associated with air conditioning. And this topic has nothing to do with air conditioning. Yet it's in section, 14.7 or so in your book. So clearly it has something to do with air conditioning, but what? We utilize the same types of equations that we use for air conditioning in what I'm about to describe, which is why this material is covered in this section on air conditioning. What I'm talking about are called cooling towers, specifically wet cooling towers. Okay. The first thing I would like to note about wet cooling towers is that they are everywhere. You see them all the time, even if you don't know what you're looking at. Every building that has a refrigeration cycle in it, which is practically every building in the world, right? We all have air conditioners. Not homes, that would be too expensive for a home, but you would actually see a wet cooling tower. Somehow you have to reject heat from your cycle through the condenser out into the environment in a refrigeration cycle. Well, how do you do that? Now, at home, we know how to do that. You just blow air across the coils on the condenser. But what if you're talking about a large industrial process like you would find in a large building like this one, or like the entire campus? You're probably aware that Cal Poly has a massive cooling water storage system up on the top of the hill. If you ever wonder what that big tank is, sometimes it's green or red or blue or whatever they decide to paint it that year. But Cal Poly generates millions of gallons of very cold water using a vapor compression refrigeration system. And that cold water is then circulated all over the campus in underground insulated pipes, which are providing the cooling for each and every room that you've ever been in here on campus. There are some exceptions. But nonetheless, it's not like there's a refrigeration cycle inside the ceiling here where all these vents are, right? What's in there are cooling water coils. That cool water is generated by a system up on top of the hill, and the heat that's rejected is rejected into the environment via cooling towers. Okay? In other words, the heat that's rejected is first rejected into a water stream, and then that water rejects the heat into the atmospheric air. Now, this is just one example. Okay? Another example would be power plants. Any steam power plant needs to have some form of heat rejection. Now, if you're lucky, your steam power plant is going to be along the coast, and you can just use the ocean water for cooling. There's a condenser in a steam power plant, right? We know that in the condenser, Well, the steam that comes into the condenser goes across tubes. On the inside of those tubes is what? Well, it's water, right? It's cold water. Where does that cold water come from? Well, it's come from the cooling tower. So we need to start looking at these wet cooling towers. I might also note that in a steam power plant, well, maybe I should put it this way, steam power plants, at least right now, represent, well over 50% of the electricity that's produced in this country. You know, up until a few years ago, 2/3 of that came from coal. Now that's down to about 40%. But we've got lots of new natural gas plants just used to generate steam for steam power plants. There's solar plants that generate steam. There's geothermal plants that generate steam. There's nuclear plants that generate steam. And every one of them, unless you're on the coast or let's say a big river, will have a wet cooling tower. Okay, so the cold water needed to condense the steam in the condenser comes from a cooling tower. What does a cooling tower look like? Well, there's a lot of different shapes and sizes, but this is a pretty good representation of a cooling tower. And basically what we have is the following. We would have water that comes in the top. The water is going to go through some sort of a distribution system. There's many different types of distribution systems. It could be spray nozzles. It could just be a big bar with a bunch of holes in it that rotates and allows water to drain down into the cooling tower. It could just be a big reservoir with like 1 million holes in it at the top that would then kind of distribute the water and allow it to sink down through the cooling tower. But nonetheless, the water comes in at the top and then the water goes out at the bottom. What is this water being exposed to? Well, air. So what we're going to do typically is take atmospheric air, and these are typically going to be counterflow types of devices. The water moves in one direction, the air moves in the other direction. That actually will maximize your heat transfer. But nonetheless, the atmospheric air is then going to simply come out the top. I will note, of course, that while the water moves itself just due to gravity, the air is certainly not going to move itself. You're going to have some sort of a fan up there. Well, but that's not entirely true either. And not that you really want to get into this right now, but there are other ways of providing a motive force to move air. There's a device called a natural draft cooling tower. If you consider that the air moving through this device is, well, it's heating up, right? Because there's warm water from your power plant or your air conditioner dropping down, cool air is coming in the bottom, so it's picking up heat and it's picking up moisture, right, due to evaporation. So the water that comes out the top has a higher temperature and a higher humidity, both of which lower the density. And we have low density air coming out that's now being exposed to the higher density atmospheric air above it. So you just basically put a big stack. Just put a stack right up here. You end up with the low density, high temperature atmospheric air coming out of the tower that then naturally rises up into the higher density air above it. That provides the force needed to move the air through the cooling tower. Some of you have seen big pictures kind of a device that looks like that. Does that look familiar to any of you? Some of you may have even seen these. These could be 600 or 700 feet high. This is the cooling tower down here. This is just the stack. Okay. You guys are a little too young for this, but when the 3 Mile Island nuclear accident happened, people got freaked out about cooling towers. I mean, the fact is, on 3 Mile Island, the biggest structures you see are these massive cooling towers. And that's what was always in the background behind all the news reporters who were basically describing, generally inaccurately, the accident that was taking place at 3 Mile Island. Well, that's true. People were scared to death. And from that point forward, well, at least say up until maybe 15, 20 years ago, people were afraid of cooling towers. You know, they thought that those were nuclear reactors. They're not. They're just cooling towers. Anyway, a little bit of history to make this more fun. So this is a cooling tower we're analyzing. We don't care what provides the force to move the air through the system. All we really need to understand is the nature of the particular process. So now what we need to do is look at the equations that we would utilize for this type of process. So let me just redraw the cooling tower without all the fluff. And let's just note that there's going to be two streams that are moving through. Let's say moving upwards is our air stream, and we'll let 1 and 2 represent the air going in and the air leaving the cooling tower. And then the next is our water stream. It moves down as you go from point 3 to point 4. Okay. Now, maybe this diagram is a little bit misleading. I don't want you to think that the air and the water are physically separate from each other. This might be called a direct contact heat exchanger. Okay, I mean it is definitely a heat exchanger. The water's cooling down, air's heating up. But there is actual mixing. In fact, that's why we call this a wet cooling tower. A wet cooling tower, the water and the air physically mix together. There's another type of cooling tower called a dry cooling tower. And in dry cooling towers, it's more like a typical shell and tube heat exchanger. The water moves on the inside of tubes. The air blows across those same tubes. There's no mixing. There's just heat transfer. Dry cooling towers are not nearly as prevalent as the wet cooling towers because in a wet cooling tower, you're taking advantage of the evaporation of water. That evaporation of water gives you a significant amount of heat transfer. In fact, if you look at a typical wet cooling tower, 70 or 80% of the heat transfer takes place simply because of the evaporation process, right? If you didn't have evaporation taking place, you would end up with maybe 1/3 or 1/4 the required amount of heat transfer, and the dry cooling tower would therefore have to be maybe 3 or 4 times bigger, physically larger than the wet cooling tower. The downside, of course, of the wet cooling tower is that you're evaporating water. You could easily evaporate 1 million gallons a day or more from a typical cooling tower in a large steam power plant. In fact, some of you might even want to go out onto the internet and look at cooling towers just by example. If any of you ever go up Interstate 15 just north of I-10, just 15 minutes from here, you look out to the right, to the east side, and you'll probably notice the giant car destruction. It's a recycling center for cars. Big thing, grabs a whole car, drops it in a shredder. It's amazing to watch. But as you're looking at that, just look one property to the south, and you'll see the Etiwanda Power Station. There's actually 4 power plants there. 2 are shut down. The other 2 are scheduled to be shut down because they're old. But nonetheless, the cooling towers there are typical. On the larger units, which are only about 300 megawatts, which is about 1/4 of the size of a modern system, the cooling towers are about 100 yards long and about 30 yards wide and about 5 stories tall. And that's just for one 300 megawatt power plant, okay? Imagine what the cooling tower would look like at a typical 1,200 or 1,500 megawatt electric power plant. Your cooling towers are going to be hundreds of yards long, stories high, massive devices, okay? Again, they're everywhere. You'll see those jumbo cooling towers the next time you drive by Etiwanda. Nonetheless, we're just looking at them as a simple little process with 2 streams, 1 tube being the air, 3 and 4 being the water. Perhaps I should say atmospheric air. It's not like we're taking the dry air out or anything like that. Okay. So now let us look at our equations. And we'll start again with mass balance. And we'll again look at the air first. Once again, I should probably use the word dry air just for completeness. Well, again, we're not accumulating any air within the system. So m dot air at 1 has got to equal the flow rate of air at 2. We'll just call it m dot air. By the way, some students might not necessarily agree with this. I mean, you might look at that and say, well, how do we know that all the dry air that goes in is going to go right back out again? Well, I would have you look at it this way. If it doesn't, you're in trouble because you're either accumulating air mass within your system. You can only get so much air in the system before the system just explodes, right? Or if you assume that you have less mass of air coming out, that means you're diminishing the mass in the system. Over time, all the mass is going to be gone. You have a perfect vacuum, and the whole system will just implode. I mean, it doesn't work that way, right? Whatever air goes in has to go out. So we've seen this many times. Maybe it makes more sense. Let's look at the water now. And with regards to the water flow, well, we know that we have 4 streams, right? 2 inlets, 2 exits. We would recognize that m dot A times omega 1 would represent the water vapor that comes in with the atmospheric air. And then we would also have plus m dot 3, so that's the water that actually comes in, the liquid water that's dribbling through the cooling tower. By the way, all those little slash marks that I put in here, that's actually for a reason. Not only do you have the spray or the distribution system at the top, but this is what we call packing, or you can call it fill, you can call it baffles. There's a lot of names for it. But basically, it's a system to increase the surface area. These days, often it's just like waveform PVC plastic. But it's a waveform. It really increases the surface area as these dribbles of water hit the top. Then they form a nice thin film on this waveform packing. And by increasing the surface area, you really increase the rate of heat transfer. Now, none of you have had your heat transfer class yet because this is a prerequisite to it. But you will find that rates of heat transfer are a function of many things, including time of contact, including temperature difference, but also including surface area. So if you don't have enough surface area, you're not going to get the right amount of heat transfer. Again, just another little tidbit as we finish our mass balance for the water. So we have air coming out. The amount of air that leaves is just m dot A omega 2. And then the liquid water that leaves is just m dot 4. Okay. And then this is often just reorganized. M dot 3 minus m dot 4 is then equal to the m dot of the air times omega 2 minus omega 1. Now, this is actually an important equation. It equals something. What does this equal? Well, let's think about it. The difference between m dot 3 and 4, well, that's the amount of water that's evaporating out into the airstream, right? M dot A omega 2 represents the moisture in the air that leaves. M dot A omega 1 represents the moisture in the air that comes in. So the only difference between the two is the amount of water that is evaporated. Now, I mentioned just a few minutes ago that in a typical large cooling tower, you could lose 1 million gallons a day of water. You need to provide a makeup water supply to that. You know, it's not like a swamp cooler where you just want to leave the valve open and maybe have like a little float valve like in a toilet or something, just so you always have water in the swamp cooler. Here, you need to continually provide makeup water, and 1 million gallons a day of water is a lot of water. You need a dedicated system. That system has to be reliable. So this is equal to the mass flow rate of what we'll just call the makeup water. Okay, this is an important parameter. If you don't have enough makeup water to operate your cooling tower, you can't operate the cooling tower. And if you can't operate the cooling tower, you can't operate the system that's using this as your ultimate heat sink. So this is our mass balance for water. And then that leaves us with our energy balance equation. This equation is going to take a little deriving, and I only have a couple of minutes left. So why don't we just leave it here for now? This will give you a chance to, read this material in your book and perhaps gain a better understanding for this particular type of device. Nonetheless, we'll continue this next time. I've got a complete example problem that I'm going to go through as well. So that's all for today. I'll see you all on Friday. Please don't forget to drop off your homework. Just put it in the pile that's up here. And again, I do have some old work, Rosales, Navarro, Gutierrez. So pick up your work, please. See you all Friday.